So I'm going to talk a little bit about ENSDF, what it goes into ENSDF. ENSDF is evaluate the nuclear structure data file. I'm not going to talk in detail about the structure of ENSDF. We'll leave that for some other time. Okay. ENSDF, you know, is a file that it has 80 character records and thousands of records. It's a file that is not indexed. It's just straightforward file. Let me see if I can move this thing down. There we go. I borrowed or stole this thing. I think it belongs to Coral Bagling. You see, ENSDF has data for over 3,000 nuclides. And each piece of data is in a data set, not each piece of data, but the data are stored in data sets. And there are three kinds of data sets: decay data sets, reaction data sets, and adopted data sets. Decay data sets have information on beta minus, electron capture, alpha, delay neutrons, etc. Reaction data on reactions. And adopted data has only levels and gammas. Levels, for each level, we have an energy, spin, half-life, magnetic moment, and quadrupole moment, and configuration if possible. Gammas, we have E gamma and multipolarity, branching ratios, mixing ratios, and internal conversion coefficients. Let's see if I remember this. Okay, let's go to the decay data. We interpret these data statistically, and we treat them statistically. Statistical treatment of data. We're going to see properties of the parent nucleus. We evaluate that and store in the file. The same with gamma rays, beta particles, electron capture, alpha particles, level structure, and decay scheme. Statistical treatment of data. Yeah. We average our data, something very, very simple. We learned that in kindergarten. But sometimes we do it a little bit more complicated. We assign weights to the data. It is 1 over sigma square. Then we study also discrepant data, and we have different methods to deal with discrepant data. The simplest one is the one that gives you the external error and the internal error. And we think that was sent to us by who knows whom, you know. Well, let me show you. This is unweighted, this is the weighted data, and here are the uncertainties. We're tempted to believe that this thing is just correct, is fine. Well, it's neither correct nor wrong. It's just assumed. Imagine that you have data where chi-square is the deviation of the sum of the deviation of each point from the average. Imagine that chi-square is greater than 1. For chi-square greater than 1, generally the data are discrepant. Well, how do we solve that? Well, if something is wrong, it's very hard to fix. We don't know what is wrong, but we assume that the uncertainties are either underestimated or overestimated. In general, it's overestimated. So we say, okay, we are going to increase uncertainties and bring this to 1. So we multiply all the values by square root of chi-square. Now, that means that, yes.
Can you give me an example of the kind of data that you would be doing this?
Or is it a half-life?
Okay.
A half-life. So a half-life was measured in Dubna.
Okay.
And and then another one in Brookhaven, Berkeley, Beijing, Sao Paulo, Brazil. And the chi-square is 3 or 5, something like that.
This is the reduced chi-square.
The reduced chi-square, yes. So we say, okay, there is something wrong here. Let's increase the uncertainties and reduce the chi-square. Now, and we say, okay, we have to increase uncertainty by 30%. Well, all the uncertainties are increased by the same value. What is the probability that in Dubna, in Sao Paulo, here in the Vatican, No, they have the things wrong by the same value. It's almost zero.
Right.
So that's a critique to the method.
And is this the standard that's used, Eddie?
It's
You're doing
used-
a lifetime
It's used by
evaluation of the
many
data?
people. Actually, we use it for ENSDF. You will see nuclear data sheets at the beginning. What is the average and what are the uncertainties? And the larger of, I think, no, it doesn't say here. It's the larger of W or W times square root of chi squared. That's the error. That's one way. There are different methods, to attack data that are inconsistent. And there is a paper by Desmond McMahon from Imperial College in London, in Nuclear Instruments and Methods, I think it's 1992, where he discusses the different methods available to attack this problem. None of them is right or wrong. It's just a method. So, in general, those methods that one used to increase the errors are not logically very well supported. But there is a method that is, we liked it very much, and the IAEA used it. It's called the limitation of relative statistical weight method. If you have data that is inconsistent, is discrepant, you cannot have one measurement that has a weight of more than 50%. Say that's too much. So you reduce that by increasing the uncertainty. Of course, you increase uncertainty. That's the only thing you can do. If you change the central value, well, you better ask the author to start measuring again this. So, but at least it's not just increasing the uncertainty for to make chi-square 1, but for a different reason. The reason is that you don't want to have one value in 30 values or 20 values that is more than 50% higher or lower than the rest. So what you do is you multiply that uncertainty by a value that will bring that number to less or equal to 50%. And then you recalculate chi-square again. And other steps, okay? This technique was used by the IAEA. And they have a program, CRP, I think they are called. And they used it there. And here's the paper that you may want to read by Desmond McMahon and his student, Rockwood. It's very good. It shows several methods used to deal with discrepant data. None of them are right or wrong. They are just add-on. Now, we used to say that if the data are discrepant, chi-square is greater than 1. Well, that depends on the number of degrees of freedom. This is n minus 1. So if you have 10, if you have a 2.3, it's fine. So if your chi-square is not greater than the critical chi-square for that data set, then you're fine. So the probability of chi-square greater than critical is less than 1% if you are below those numbers. So 1 is an exaggeration. The number 1 is, you see, when you go 1.7, more than 30 things, you go to 1. But we always say, let's multiply by chi-square to make it 1. Another thing that we evaluate, and we store that also in ENSDF, are the properties of the parent nucleus. The level energy, spin and parity, half-lives. Units, well, there you are. The Q value, we use a Q value deduced by Audi and his people. Now is published in the Chinese physics. And there is a program, a Q value calculator at Brookhaven, where you enter all the data and you say, well, I want the Q value for cobalt 50, cobalt 60, and it gives you the Q value there. Theoretical values are from Muller.
Okay. Can you describe for a minute what you mean when you say a level energy of plus X? What is the
It means that they don't know whether it is the ground state or not. So we use in ENSDF something we call plus X. And if it comes to worse, could be plus X, another one plus Y. We know that is there, and sometimes we don't know whether it's above or below.
Is there any way to record, however, you know from the data set that X is greater than Y? So if you have multiple floating.
Only you can do that in a common car.
But there's no way to do it formally.
Not that I know. Okay.
But sometimes you're also going to have, you know something's the isomer, it's published that it's an isomer. It's not gonna be
Yeah, but the word isomer, do we know that that's the isomer and not the ground state isomer and that's the ground state?
the one piece we
Yeah, you see, that's the problem. You don't know
Which one is what?
which one is which one.
Isomer is ground state or the ground state is isomer?
can
Yeah.
connect it to.
Yeah.
So just to be clear for the students here, what we're talking about is that you can have levels that we know will exist in a given nucleus. We know that they've belonged to the nucleus. It could be because we've seen decay into that nucleus, or we've got a strong measurement we've made the nucleus in an experiment.
Yes.
Evidence at this level as part of the parent level where a transition was going between. But we may not know whether that level is the lowest level in the nucleus, the ground state, or further up. And unfortunately, what you're saying also is that if we have any information about that other, for example,
Right.
ones, we can't record that in any way other than the
No, in a common car, that's the only way that I'm aware of.
Right.
Okay. So, gamma rays. What do we evaluate of gamma rays? We evaluate the energies. We use averages for energies. Relative intensities, I'll talk about that. Multipolarity and mixing ratios, also, we evaluate that and store. Conversion coefficients, those are theoretical ones. In special cases, when conversion coefficients are very precise, then we store the experimental values also. And total transition intensity, which is I gamma times 1 plus alpha, is the sum of the photons plus the electrons. Absolute intensities, we store absolutely correct absolute intensities, okay? Or some other people call them emission probabilities, which I like very much that. And we should aim to determine absolute intensities, even if the author does not give an absolute intensity. We try to do something to obtain that. Sometimes we can do it, sometimes we cannot. There's not enough information from the case scheme or from other.
Are you going to go into that in some detail?
Yeah, oh, yeah.
About that? Okay.
Yeah. Gamma rays, energy, weighted average, is what I said. Now, if they have very precise measurements, bent crystal, we use that. We use recommended standards for energy calibration, those of Helmer and van der Loon, published in the year 2000.
What's bent crystal?
Is a special detector that uses diffraction, to determine the energy of the radiation. Extremely precise. It's not keV. It goes almost into EVs.
Yeah.
And its resolution is amazingly high.
You have to be very far away.
You have to
use
be
the crystal
far.
plane. The crystal plane, and it's done at a specific angle, and you sit some distance away, and you look at the crystal is
Yes.
a gamma ray source.
Yes.
There's a lot of gamma rays. It's a very intense source.
Sometimes you do want to have, you may say, well, why would I want to know the gamma ray energy better than 1 keV or 0.5 keV? Well, sometimes you will. There is a case of an isomer, the lowest isomer ever known in thorium-229. It's an isomer of about 5 to 7 EVs. Then you need bent crystals to determine that by differences in gamma ray energies. But those are a few cases, but you do need those things. Conversion electron energies, etc., multiplets. Relative intensities. How we have, let's say, 3 measurements of gamma rays emitted by a nuclei. And we get the gamma rays there and the intensities. Okay, we find the averages, and that's what we report. However, is that the best that we can do? No, it's not the best. There's something else that nature is giving us. The ratio of the intensities of those gamma rays for one decay is fixed, is part of nature. So in this gamma ray, for this nuclide, and this nuclide, the intensities are all relative to one of those, 100 we call it, but the ratios should be the same. And that's another story. To do that, you have to find the average of the intensities, but you have to minimize everything. Do a minimization to include the branching ratios into this calculation. That's not simple, and Rick Firestone did that. He wrote a program called Gamut that now is being processed in Vienna by the IAEA, and is going to accept data from ENSDF as an input data. This book, also Rick Firestone, has the gamma ray intensities there processed that way. You have 3 or 4, you find the averages, but you include the condition that the the ratios should be the same. And that is not simple. It's a complicated thing. It's a nonlinear minimization. Okay.
First of all, I'm sorry if I asked a lot of questions, but it's great, and I want to make sure I get it all. So these are all just the intrinsic intensities, the relative intensities.
Oh, yes.
Coming from
Not
say,
absolute.
given level.
Yes.
All absolute.
No, not absolute. Or well, you want absolute too. Yeah.
And so this is clearly amenable to a decay data set.
Yes.
Now, if I populate different levels with different intensities in a reaction, okay,
Oh.
is there any way to catch that information in ENSDF?
No,
See what I'm saying?
That you have to give by level. You have to give the intensities, because different reactions populate the levels differently.
Of course.
That's the problem. No.
And there is no way, is that information,
Not,
in a paper, is that information in ENSDF in any way?
no, the only thing I know is you put it per level. This is the branching, and that's it.
But that's a branching, that's not.
Yeah.
That's independent of how
No,
well
it's independent because you change a little bit the energy of the projectile and everything changes.
Exactly.
Right.
Well, then it means that information is not present in the ENSDF file, which
Is not known.
not even as a comment necessarily,
Yes.
you're saying.
Okay, so we call 100 usually to be 1000, the most intense gamma ray. We use a limit from expected but unobserved gamma ray. Use total intensity, transition intensity, this is the only quantity measure or deduced from transition intensity balance. If alpha t is known, that is a conversion coefficient, then you divide by 1 plus alpha t and you get the photon intensity. Limits are acceptable, but this way of writing it is much better because you can use it. Intensity from an isomer in the daughter nucleus should not be given if such intensity is time dependent. Let's say you have 10 days, the parent, and 1 day, an isomer. You have gamma rays from, you cannot give those intensities because it depends when you measure them. I think, oh, did I? Oh, let's skip that. Here is the case. Now we have an isomer, 10 days, 1 day. These two gammas, they grow like this. And then when they reach equilibrium, then you can give them. But it's possible. ENSDF is a very liberal file. You can put whatever you want, but usually you don't give that. What you give is the half-life of the isomer and maybe the intensities of the relative to the isomer when you report the isomer. Otherwise, you have this problem. You cannot give intensities in this region.
So I'm sorry, can you say this again? So how would you record the intensities of gamma 2 and gamma 1?
You won't.
You will just leave
Leave the energies only. Do not give these intensities under this decay. Now, under this decay, yes, if you have an entry for the isomer, then you can give those intensities.
So if I understand right, what we do is I would make a second data file.
Yes,
So we-
yes, it's another data file.
A different data, yeah.
It's a different data set. You cannot give that.
Does this signal familiar to you guys from the class? We went over transient and secular equilibrium. That curve should look familiar to you.
Yes. Oh, you
We did this,
explain
we
to
did
them
exactly
this.
this. Yes. Well, I didn't explain how we did it in ENSDF because I didn't
This is
know.
a typical case on technetium 99. Technetium 99 is like this. Multipolarity mixing ratio. We can deduce that from conversion electron data. We should explain how the intensity of the K electrons and the gammas were determined. We can also get from angular correlations this, but notice that in this case we can know whether it's just dipole or quadrupole. We cannot tell whether it's electric or magnetic. Oh, this is too long. It's just algebra. If you have an E2, M1 plus E2 transition, and you get the conversion electrons, you can determine how much is M1 and how much is E2. That's all. You can determine delta with a little bit of algebra there. It's very simple. And you determine the value of this delta, and M1 is 100 over 1 plus delta square. Percent E2 is 100 of delta square over 1 plus delta square. This is a typical case. We do this very much. Sometimes authors do not give this. They say it's M1 plus E2, but it's our work to go over this and do it. Determine how much is the percentage. Some authors, all they want is to publish their paper with, say, this M1 plus E2, and that's it. But if the data are there, we have to try to get those values. This is more about multipolarities. This is just only telling you that it's waiting for someone to discover monopole transitions, magnetic transition, to get a Nobel Prize. So it's E0. If
You
it
guys
is
should
zero,
know this.
zero.
This is what you're going to do next week when we get there.
Is that
Please
right?
go ahead.
Yes,
So,
yes.
you're doing
So
the job.
you don't have photons here, you have electrons. 2 plus, here you have electrons and photons. You see, is it the sum and the difference. L, the angular momentum is between the sum and the difference. 1/2 to 1/2, the same thing, is E0 plus M1. Here is M1 only. 1 plus to 0 plus gives you M1. It's between 1 and 1, L equals 1. And 3/2 to 1/2 is definitely M1 plus E2. It's not pure E1, M1. Internal conversion coefficients. We don't give, in general, internal experimental values for internal conversion coefficient. We use calculated ones. Go ahead, Leo.
Just backing up a slide. You said that you try to quantify how much M1 and E2 it is.
Yes.
But in the experiment, isn't that pretty tough to do? I mean, don't you need to determine the angle at which it's scattered? I mean, not all experimenters.
You're talking
Taking
about
a calculation.
angular correlations or angular distribution, that kind of experiment? Oh, yeah, that.
When we do try to do that, in experiments, we would have to measure angular variations either at one gamma,
Yes.
whether that's a correlation,
Yes.
or absolutely it's a distribution. And you'll find that often the electromagnetic transition has both characters involved and in a different amount, which we represent this mixing ratio of
Yes.
delta. We try to measure it, or we don't.
Usually from
Is there
conversion coefficients or subshell
Two
ratios.
angles you put the detectors at to measure that?
Some people vary the angle continuously. They'll run the detector on a goniometer and look at that sport. Some people have fixed angles, so they run the experiment after the work today. Very valuable information.
Shall I move this?
Well, especially the case transfer that I know, it's just anyway, we can't. Unless we have conversion.
And what's the conversion electron tell you?
The ratio of
In general, as multipolarity of the transition goes up, the amount of time, the fraction of time that it would be, it would go by internal conversion, which means electronic transition, liberating an electron, goes up. And there's different values for electric versus magnetic transitions. So you can measure the ratio of the intensity from gammas versus the intensity from conversion. That's a huge piece of information. That means you need to see not just photons, but photons and electrons. That's a much more challenging experiment to talk about than.
You have to calibrate the detectors, both, because they are real intensity that you divide.
You can also make electrons for different shells. One fluoride, one for
That's right. So if it goes into the L shell, you'll have 3 values, because there's 3 different L shell conversions that can go through the different energy, and the SPI. Okay, and so you can get all this different information.
Yeah, I didn't show here, but actually, if you can measure subshell ratios, sometimes you can determine also molecularities. Just from subshell ratios with no photons.
So if they don't provide all this analysis, you have to go back and do it.
Well, yes, go ahead and do it. Sure.
The evaluators?
Yes. The formulas are very simple. They're all written in little manuals.
If that information is in the paper, if I publish something where I looked at conversion electrons, okay, I do type of information. If you get conversion electrons,
Right.
and my detectors are really close, and everything gets washed out, so I then
So here's a question. So let's say you're evaluating a new fix.
Yes.
And you see, you read the paper that somebody has done, and it's a beautiful paper,
Yeah.
and they haven't included a valuable piece of information. For example, they have an electron, a mini-arm spectrometer that measured conversion of electrons,
Yes.
but they haven't reported subshell
Ratios.
ratios, and you think you could use that. Do you as an evaluator go and call people and ask them for information? Do you call the authors up? And try to get this?
Yes. Occasionally we call them, and I understand you called them once. Remember? Very,
Recently.
yes.
Yeah, that was for the data sets, but it was not for the electron measurements.
No,
for
not for other
things.
reasons.
But
But we
always
call
we
authors.
communicate with the authors after the publications, and we get more information, and we incorporate that communications to our file.
Yes,
Yeah.
we do that.
then on the other side of it.
Right, and of course, the interesting thing here is that the author had another agenda in writing the paper.
Yes.
So they just might not have dwelled on this, even though it's extremely important information.
He needed it for something else, not for what you want.
Right.
And that's the reason. Now, shall I continue?
Oh, yeah, I'm sorry.
Internal conversion coefficients. We don't give experimental values in general, but we do give them if they are very precise. Precise and accurate. We use theoretical values. The latest one are Browne and Browne and the Russians in year 2000. And Tibor Kibedi, I don't know if you know him, is a scientist who works in Australia, is an excellent physicist and programmer. And he programmed BRIC, is Browne something, conversion coefficients, a program that we use to interpolate conversion coefficients for different multipolarities and energies, theoretical values. And we found that the precision of that, the agreement with experimental values is within 1.5%. So there's no need to use experimental values anymore. They are very accurate.
There's another program, I guess, older, HISC, whatever.
Yeah, HSICC,
Is that,
Henry Seltzer.
okay, is that not, in favor anymore?
No.
I think that had uncertainty of 3%, but this one is
One
improved by
and a half
1.4%.
Okay.
Uncertain means agreement is
Yeah.
within 1.5%.
So I never knew that band Raman, that band was a name of a person.
It's a thing.
I thought it was like electronic transition band.
Or Bay Area.
I bet there's actually a person who's the IM band.
Person's name. And
I
think
knew
it's-
Raman, but
Yeah. Raman is from India and Ban, I think, is Russian. I think,
well,
because the other one is Russian. It's a lady, the other one, I believe.
it's a great name to have.
Now, I mentioned that some experimental values we do want to give. For instance, very precise values, less than 1.5%. That is data that is important to keep. Another data that is important is conversion coefficients that do not agree with theory. with a simple theory. You need a more complicated theory. Some that includes penetration effects of the of the atomic wave functions into the nucleus. That's the case of protactinium-233 beta minus decay to uranium-233. And for instance, the experimental value is 0.64, and these values, the theoretical values, are completely different. There are worse cases than that. Mix E0 transitions, for instance, we do give those if they are precisely measured. Look at this one, 2.4 plus minus 0.8. The theoretical ones, M1, E2, are totally different. It's because they have E0s. Total transition intensities. This field should be used only if the measured quantity is that. Otherwise, try to avoid using this field. Usual cases are when you deduce from transition intensity balance. You have the levels and you have the gamma rays and the electrons. So you deduce the value of the transition from a balance. Then you get this. Or if you know that the number of electrons that you have there are negligible. Or if not, but conversion coefficient is known, then you can deduce I gamma. I gamma is always better, more useful than total transition intensity. Total intensity from transition intensity balance. Well, this is very simple. Let's say this red transition. We want to know what's intensity of this. Well, it should be equal to the sum of this plus that if there is no feeding here. And that's what it is. If alpha, the conversion coefficient is known, you divide that by the conversion coefficient and you have the photon intensity of this. This is just very simple.
That's not relevant.
Oh, am I doing? Pardon me?
Well, that's I guess the
Am I going to?
assumed.
Oh.
Because you're missing a lot of transitions anyways.
Yes, yes, but it has nothing to do with the previous one. It's a new talk. It's a new case. This the one I'm doing now. Absolute intensities. Some people call them. What did I say before? Emission probabilities. No? The absolute intensities per 100 disintegration of the parent. Measure photons, like per beta plus or alpha. Simultaneous single measurement or coincidence measurement. You can put two detectors, one for betas and one for gammas, and measure simultaneously. And you have to know the efficiency of the detector. The ratio gives you the absolute. Or you can do 4 pi beta gamma coincidences, and you can get the absolute intensity of that. That means emission probability.
So let me ask you again about this coincidence. So I can see how if I have a decaying set, I may have radionuclide is decaying.
Yes.
And I have the efficiency well specified for my detector.
Yes.
And I can give you that will give me the intensity of that gamma ray that I observe.
Yes.
If I have another tag which tells me that like this was beta decay,
You need another detector. Yes, yes.
then that would give me this ratio.
Yes.
If I do not have this information, then you cannot specify anything in this.
No,
Is that
no.
correct?
You need to have the betas somewhere.
Right. Or the alphas.
Or the alphas.
Right.
The alphas are even better. I'll tell you then why. For instance, this is an absolute intensity. You have a 2 MeV level, has practically no electrons, and you know that you have only one beta that goes here. The intensity of this is 100%. You don't need to measure that. You're saying that. And that's it. It's 100%, has no uncertainty at all. There are no electrons, or the uncertainty is so small. You can also have simultaneous measurements. Beta, gamma, measure simultaneously the ratio, and you get the absolute intensities. Number of photons per 100 beta disintegrations. This is very common also. Now I will say a few words about beta particles. What do we store or record about beta particles? We store the relative intensities and, if possible, the absolute intensities, the average energies, which are calculated actually. the maximum energy only if it's very precise. Otherwise, we use the Q value given by Audi. And the log of T's, we calculate those. Beta particles, oh, I already said that. You would give only if the experimental value is very accurate, we give the maximum energy. We do not give average energies. The program calculates that, log of T. Absolute intensities per 100 decays of the parent nucleus. We give that. We give the experimental value only if it was used for normalizing the decay scheme. Give absolute value deduced from gamma ray transition intensity. That's what we do. There is a program, GTOL, gamma to level means GTOL, written in Oak Ridge 100 years ago, and something like that. But still good, very good. And that calculates the transition intensity balances level by level. And those are equivalent to the gammas, the betas. Log FTs, once we have all those feedings, we calculate log FTs, are useful for spin assignment or to verify that the assignments that exist are consistent. Electron capture, same thing. We measure the relative probability, the absolute probability, relative shell, subshells are theoretical. And then we calculate log FT. Electron capture, there you go. The feedings are deduced from the transition intensity balance, the same as for betas, except that here we say we have electron capture and beta plus, if there is enough energy for beta plus, of course. The program log FT calculates from theory subshell ratio probabilities. And we give in comment the X-rays, the measured X-rays. And these are, well, you will see later on, these are very useful for normalizing the decay scheme. If you know the X-ray intensities and you know something about the decay scheme, you can determine the normalization is a factor that you multiply all the other radiations by and gives you the absolute values. That means the emission probabilities. And you can deduce that from the X-rays. I'm not going to talk about alpha particles today because that's a horse of a different color and it's very long. We'll leave this for some other time. But we report the energies, the relative intensities, and the hindrance factors. Just want to tell you that alpha particles are very good for determining normalizing decay schemes because they are discrete. It's not like betas as a continuum. You know, you can see the alpha particle to the ground state. You know, it's 3%. Then you can normalize the decay scheme. With beta, it's hard.
So this was my question, and for the data, you have this tagging efficiency, which I understand you need if you do absolute efficiency.
Yes.
But you don't ever see it all the way to zero.
Right.
You never see it all the way to zero.
Yeah.
So what do you do if you have,
Well,
does the evaluator make a Fermi-Curie plot and say, where does this thing intersect zero?
the evaluator has to use, if it's possible, whatever is there. But sometimes if they give the beta intensities, well, they don't tell you how much goes to the ground state. It's very hard to know. With alphas, it's different. Alpha, you have beta is a horse of a different color also. So you have to live with that.
I mean, this is my question about, because you could just, at the end of the day, there is some minimum energy in the experiment that you will see the beta particle down to.
Yes.
And once you get below that, you may still see the gammas coming, but you will not see the beta any longer.
That's right.
And so if you're setting a relative efficiency by doing a beta gamma coincidence,
Yes.
you will still have gammas that don't have beta corresponding.
Right. Because they go to the ground state. That's why you have no beta corresponding.
Right, or I just experimentally, I just have a limitation.
You don't, you're limited. Well, you
For the
cannot do it.
beta that I don't have the gamma.
Yeah, you cannot do it. That's it.
The efficiency can be very different from different energy.
Of course, right. So
things to a high energy energy levels are not going to give any data stability.
that's right.
There's no speed.
But even if you have a fixed energy that you're coming into, you're looking at it, below a certain fixed excitation that you do in the donor nucleus, below a certain beta energy, I just don't see the data anymore because it got stopped in the target or.
Right.
I can see why you like alphas.
Yeah, but the beta to the ground state are the ones that have the highest energy.
Right.
That
And
because
there's no gamma.
because it's not a discrete line, it's something continuous, it's very hard. Very hard. Okay, I won't talk about alphas. We'll leave that for some other time. Level structure and decay scheme. What do we give? We give the level energy, the spin and parity and particle configuration if possible. Well, everything is possible, of course. Level half-life and the decay scheme normalization. That means what do you have to multiply the intensities by to get absolute intensities, to get emission probabilities. Here is something very simple. The absolute intensity of one gamma ray is known. Normalization. Let's say this red one is known. Well, if you know this one, well, you know the relative intensity and the absolute intensity, well, you determine a normalization factor, which is the ratio between the absolute to the relative one. It's a different scale. And the uncertainty of n is just the sum of these two uncertainties. Then gamma percent of 1 is equal to n times this. So this is very simple. From decay scheme, let's suppose we have this case. We know that it's like that. There's one beta that goes like that, decays to that. So then the normalization factor times this intensity times the 1 plus alpha should give you 100%. There's nothing else. We know that. So then you can get how much is the intensity of I gamma is just algebra and the uncertainty. You can propagate that. Is all the uncertainty comes from, let me see if I'm right what I'm saying. It comes, yes, from the conversion electrons. Now this is a little bit more complicated. Okay. We have this decay scheme. What is the normalization factor? Well, the sum of the two intensities that go to the ground state gives you the normalization factor. Because here you calculate this, the intensity that comes here is this minus this, the one that comes here is this plus this, and let's assume there is no feeding here, then you sum this and you get this plus this should be equal to 100. So you multiply by 1 plus alpha, and you get the different intensities of gamma 1, gamma 2, and gamma 3, n times that. Now you have to calculate uncertainties of this. You want to know the uncertainty of I gamma 1, I gamma 2, and I gamma 3, absolute. Well, you use 1.5% uncertainty in alpha 1 and alpha 3. We know pretty accurately those theoretical conversion coefficients. And then you have to use your knowledge of calculus because you're mixing different I gamma 3, I gamma 1, I gamma 2, all mixed. So you look at nuclear instruments and method. This publication will show you how to do it. Or you use the program gaps. I didn't talk about the programs today. Some of the time we'll talk about all the programs that are available. This program, you put the intensities of, you flag the intensities that go to the ground state. And we'll go and calculate the absolute intensities, provided you either give a feeding to the ground state or put 0. Nothing.
And so you just have to tell it that this is a transition that you believe goes
You
to
have
0.
to tell it. You have to tell it. No? And then once you know that, for instance, here, you see, here this ratio cancels. But here you have gamma 3 over gamma 1 and gamma 3 here. So you have to propagate that properly. It's not difficult, but it's tedious. Oh, this is equilibrium, very little. Let's suppose this is an equilibrium and you know this, okay? So you can get the normalization factor using the last one. Assuming the first one is the longest half-life. This is not very important. Okay, here is something that is very interesting. If you have annihilation radiation, it is known, a paper publishes annihilation radiation of a beta electron capture plus beta plus decay. And you don't know how much goes to the ground state. You can determine that from the annihilation radiation. How? Let's suppose the annihilation radiation is this value, I. you calculate the intensity imbalance for each level and call it Xi. And you use the theoretical ratio of to the ith level of beta plus and electron capture. So then this Xi, the imbalance, is you can write it as a function of beta, the beta plus and the ratio. And you determine how much is beta plus. It's just algebra. Now we know you have to check that all the annihilation comes from the decay, from the electron capture from the beta plus decay. If you have very high energy level gammas, those can create pairs and produce also annihilation radiation. Fortunately, very low.
And what do you mean by theoretical ratio? What theory are you employing to do this?
I don't know, but there are theoretical ratios are available.
Or the beta plus compared to
Yes,
electron
yes,
capture?
yes.
Or
Yes, you see these ratios, electron capture over beta plus.
And that just takes in, do you have the energy then Z, I guess?
Yes, you have to put the energy in. The level energy is Q value minus this level energy, that gives you. Yeah, and the Z, and that will tell you how much is the ratio. This ratio, this over this. Once you have that, you're done. Because for each beta plus, you have two 511s that go like this. So 2 times the ground state feeding with 1 plus R0, you know, the 2 times the beta plus feeding plus the summation of all the other feedings there times R divided by 1 plus Ri should be equal to the photon, to the annihilation radiation intensity. And once you know this, you solve this equation for the feeding to the ground state, x0, and then you put that the sum of all the gamma rays plus x0, the one to the ground state, should be equal, times n should be equal to 100, and you determine n. So 511 radiation is very, very useful to determine the absolute intensity of the gamma ray. Extremely useful, and sometimes authors do not use it, they just leave it like that. And if they get the intensity to the ground state from other things, from analogies with a nucleus that is very close by, something like that, well, you can verify if that is correct.
So to be able to use that, you have to be pretty
Pardon me?
confident. To use this, you have to be pretty confident you've got most of the levels that the beta is to.
Yes, yes.
If
You have to be
miss a
pretty
lot of those,
confident.
You're gonna be off a lot.
Yes, but you have to be confident of the transition intensity imbalances. That's what you're saying.
Yeah, that you've got most of it.
Yes, yes. But you get, from that, you get the normalization of the decay scheme. You can calculate the emission probabilities using this. And something similar happened with the X-rays. If you have K X-ray intensity, and from a decay of electron capture plus beta plus, you have that. And you know, as usual, the ratio between electron capture and beta plus from theory, and you know the transition intensity balance. You can calculate how much is the feeding to the ground state. The X-rays are, oh, this is a fluorescence yield. Is a fluorescence yield time pK0 is the fraction of the decay of the X-rays that go to the zero shell. K0, Ki, to the zero level, the ground state level, I'm sorry. The sum of this should be equal to the intensity of the Kx rays. So you determine the feeding to the ground state. Once you have that, the feeding of the ground state plus the gammas plus the conversion electrons to the ground state times n is 100. And you solve equation 1 and equation 2, and you get the normalization n. So X-rays and annihilation radiations are very important. If you do have already a normalization to this, the X-rays are good for you to verify that everything is correct, that there is no error. Yeah.
How do you sign systematic error?
Oh, no, this,
No,
that's,
no,
no, that,
we don't do that.
systematic error means something is wrong. That's
Sure, because you're not gonna see all the levels.
Well, probably, yes, you don't see all the levels. You say, well, there are levels here that we don't see, and maybe that, but that is guessing. That is just guessing. And systematic errors are very difficult. It means that something is just wrong. So the level structure, let's put all together. We deduce the best gamma ray energies and relative intensity. Relative intensities at the time being are obtained only by averaging. But in the future, we hope we could use this program of Rick Firestone to include the ratios, the conservation of ratios. We calculated conversion coefficient with Rick, the program that Tibor Kibeti wrote. In the old days was Heger and Seltzer. We normalized the radiation intensity to an absolute scale using GAPS, the program that I wrote. Deduce level energies and decay branchings using GTOL, a very old program from Oak Ridge, still useful. And also you calculate log FT values using this program. And sometime we'll talk about alpha decay hindrance factors, are something equivalent to log FTs. Now, before I finish this, just so you will get a little bit of a flavor of an ENSDF data set. This is an ENSDF data set for the decay of xenon-131, the isomer, IT decay. The records are 80 character records for obvious reasons. And every record has the name, the symbol of the nuclei. This means that it's a gamma ray and it's a common card on the gamma ray on the multiplarity. This is that. All the ones that have a C are common. P means the parent. The parent has an energy of 163, which is the IT level, the spin, and the half-life. These are normalization factors we will go over. This is the one for the gamma rays. You multiply the gamma rays by this, the intensities, and you get normalized those. And here it says where that normalization factor was obtained from. Then comes the level cards and gamma cards. The first level, the second level, which happen to be the isomer, in this case, the parent, the gamma ray with the intensity and the multiplarity, and this is the conversion coefficient. And then a comment where the energy comes from. I tell you, this is just for you to see a little bit of ENSDF.